Okay, so today we're going to finish up Chapter 5. It's actually going to be pretty quick that we're going to finish up Chapter 5. And then we're going to go on to the last chapter of the book. Chapter 6 is going to discuss some really interesting, geometrically heavy ideas that are a lot of fun. I always look forward to. But let's finish up Chapter 5 first. So it's arguably this last section is just about notation. But there are some ideas behind the notation, and I wanted to make sure to give you all a rough description of what those ideas are, and that's where this notation comes from. So I'm going to start off with vector line integral. Okay. Talked about those recently. And let's think about the vector differential there. And what do we know about the vector differential? How can we write that? Well, here's our sort of easy formula for the vector differential. Dx is x prime dt, and that's pretty familiar, believable, right? But let's now take x prime, and let's expand out what we know about x prime. And now let's plug that into there and see what this formula becomes. And that purple formula then becomes this. Now, no big deal. Nothing in here is too surprising, but I just want to point out that this brings up the question of what we should interpret from the individual coordinates of the dx vector. How should we interpret, one at a time, first, second, and third coordinates of this vector differential? Well, the notation almost kind of screams what we should call it. We should call that dx scalar, because look at it. It's dx dt times dt. What else are we going to call it? Right. And that's perfectly fine. I want to give you a different point of view, though, on why we would call it dx, or a different sort of interpretation of our calling it of dx. Just because this interpretation I'm going to give you is going to extend more naturally when we start doing this with vector surface integrals. So, as we often do, something we're doing with vector line integrals, we want to do with vector surface integrals. We want analogies to extend. So, that being said, instead of thinking of the vector differential here, there it is, there's our dx vector. Instead of thinking of its first coordinate as representing the change in just the first coordinate. It's a very natural interpretation. I mean, the dx vector represents the change in all the coordinates. The first coordinate should be the change in that first coordinate. Let's take a different point of view, though. The different point of view I want to take, I'm going to draw a picture down here. And that is, there's your vector differential. This is a two-dimensional picture just to make it easier to draw, by the way. But so there's your vector differential. And I want to think of dx now as representing the size of the projection of that little piece of curve. So don't think about it now in terms of changes. Think about it in terms of sizes. So the vector differential represents that little piece of curve sitting up there in space. If you were to project it, look at its shadow down here on the x-axis, that shadow would have a certain size. So that's the way I want to think of dx. Now, I've swept a little minor issue under the rug, and that is that dx could be positive or negative. Sizes can't. Sizes are always positive, right? So if dx is negative, how are we going to sort of relate that to this idea of the size of a projection? Well, I'm going to do that by thinking about orientations. Specifically, if the curve is like this, and notice which direction it's going, if you were to infer, in looking at its projection, a corresponding orientation on the projection, and if that direction is opposite of the direction that the x-axis points, then I'm going to say that this little piece of curve projected onto the x-axis kind of backwards. Okay? And the minus sign in dx I'm going to interpret as indicative of the fact that it projected backwards. So the size of dx represents the size of the projection. The sign of dx represents the the direction, the sort of the rightness or wrongness, if you will, the forwardness or backwardness of that projection. Okay. All right. Geometric point of view. So now let me, here's that observation. Now what can we do with this? Well, recall, here's our vector line integral, old news. The vector field F has certain coordinates, so we're going to call those P, Q, and R. It's fairly standard choice, seemingly a little weird, but that's very standard to call the coordinates P, Q, and R. It's just the individual coordinates of the vector field. And now, notice we can also break down the coordinates of our vector differential. Our vector differential now has coordinates dx, dy, and dz, for which we have a natural geometric interpretation. And at this point, here's the new notation. It's not such a weird thing, really, but if you just take this dot product and actually crank it out, I mean, do the dot, this times that, plus that times that, plus that times that, which we can now do because these things both have coordinates. That dot product turns this integral, namely that integral, into those three separate integrals. And this then is the new notation we have for representing a vector line integral. Awkwardly, we're writing stuff down that we're combining notation that we've never combined before. We've talked about line integrals over a curve. We've talked about dx, dy, and dz before, but we've never talked about a line integral of a function dx. And this is a totally new kind of integral. This as a single object, we've never talked about before. Right? We're not multiplying a function times ds. This does not represent the length of a piece of curve. This is not a vector line integral. This is not like a dot product with the dx vector. Not at all. Right? This single integral by itself is a fairly weird construction, really, at a glance. Okay. So we do need to write down a definition of what that kind of thing means. It's just exactly what we just got through talking about. Specifically, dx is just x prime dt. We're using dx here in the way we've always used it before. Just need to write this down as a definition to define that new kind of an integral. So just be aware that this notation is out there. It's not even all that rare to represent a vector line integral. Sometimes you'll see it written like that. So if you see that, just make sure to interpret correctly, interpret appropriately, that a sum of three integrals like this, what that means is that these integrands, P, Q, and R, are the individual components of the vector field F in a vector line integral. Does that make sense? By the way, let me go ahead and mention as well, it's tempting to look at these two notations and think, well, which one do I like better? Well, gosh, I like this one better. Right? I like this dot product notation because it communicates so much, so efficiently. It communicates, hey, look, there's a vector field we're interested in. There's the vector field right there. And there's the vector differential that describes the little piece of curve over which I'm interested in doing a dot product for whatever reason. And it's very compact. There's a lot of good things about this dot product notation for vector line integrals. FYI, in contexts that are beyond what we can do in Math 212, this notation actually really useful. This is closely suggestive of a much more sophisticated object called an integral of a differential form. And they're extremely powerful things, much more general things that you can do with differential forms than you can do with this other point of view on line integrals. And this is pretty much what integrals of differential forms look like. So this is not just some sort of inefficient, outdated, pointless notation. It's a pretty legitimate notation. It's just that for our purposes in Math 212, the one on the left here is really going to be the one we're going to find the most being used for. But you will see this out there, and I wanted you to know what it was. Okay. So let's do the same thing now for surface integrals. Here's a surface integral. Let's talk about this vector differential. There's our formula for it. Now, let's focus our attention now on capital N. Right? It was capital X that it was X prime that we looked at back in the previous subsection. Now it's capital N. They play analogous roles. So let's try to reproduce what we did in the last section. Expand capital N in the way of what we know what it is, and let's try to work out the individual coordinates. We've never actually done this before. I don't know if you thought that was weird, but we never have expanded the individual coordinates of the capital N vector. So capital N, you'll see here, is a cross product. It's a cross product of XU and XV, each of which has coordinates we can write down. We can crank out that cross product. Let me refer you back to Chapter 1 on how to compute cross products of two vectors. It's a little determinant, symbolic determinant you write down. And no surprise, when you work that out, the individual coordinates of capital N are little 2x2 determinants. And don't forget this notation here is a little shorthand notation for a 2x2 determinant of a matrix of partials. And in fact, that's exactly what turns up. If you work out this cross product, multiply it all out, each individual coordinate happens to be a 2x2 matrix of partial derivatives. Okay, so punchline then, that's what the individual coordinates of N look like, keeping in mind that what we want to talk about is the ds vector. The ds vector is N times du dv, so you get these coordinates times du dv so, and therefore this is what your ds vector looks like in general. Now let me flash back a couple pages back now. We found ourselves in a similar position talking about vector line integrals. The vector differential, expanded out, looked like that. And then we asked the question, what does that individual coordinate mean? What should I interpret from this individual coordinate? And we had a ready and convenient answer to that. That's dx. Right? Now, we find ourselves wanting to know, what does that mean? What is that individual coordinate of this vector surface vector differential? What does that individual coordinate mean? And we don't really have an immediate answer. The closest thing we can come to understanding what this means is to observe that this factor here, we have seen it before, right? That came up, in fact, the notation itself originally came up when we were talking about change of variables. You all might recall. So it's going to turn out that we're going to be able to make an interpretation of what this coordinate, one at a time, all three of them, but I'm just going to focus on one of these. Actually, come to think of it, the ones I have pictures drawn for are this one. We're going to make sense out of what this coordinate looks like geometrically by interpreting this yellow highlighted factor as a change of variables stretching factor. Okay, so now what's a little counterintuitive is if we were to interpret this as something involving a stretching factor, we would need to have x and y as functions of u and v. And we don't really. Right? What we have is x, y, and z as functions of u and v. So I want just x and y. I want to throw z away. Forget z. Right? And interpret just x and y as functions of u and v. So can I do that? Is that legal? Are you allowed to do that? Sure. It's a projection. Let me just focus on this picture first. If you have x, y, and z, and you say, I don't want the z anymore, I want just x and y, you're doing a projection down into the xy plane. So, altogether, we started off with x, y. This is our parameterization. X, y, and z are functions of u and v. This is how we understood the surface in the first place. And now we've decided that we want to throw away the z coordinate, effectively projecting down into the xy plane. Okay, so the thing that we find ourselves looking at, this coordinate here, that coordinate says I'm going to multiply du dv, that's a piece of area in the uv plane. I'm going to multiply by the stretching factor of the function that views x and y as functions of u and v. Namely, I'm going to multiply by the change of variables stretching factor there. So this, very naturally, is that area. Oh, whoops. That area. Everybody on board? And I claim, even though one last little twist I'm going to put on this, but this is actually going to end up being very analogous to what we saw in the single variable version. So specifically, that's last observation to make is that that area, the image of the projection, well, I can just view the projection over here in XYZ space. I don't have to view it as a composed function. I can just literally view that as how big is the area in the XY plane that I get when I take the piece of surface in question and project it down into the XY plane, like so. Look how familiar. When we were talking about in the single variable case, we looked at a length of a piece of curve and talked about how big is the projection down onto a particular axis. Here, we're talking about a size, an area in this case, of a piece of surface, not curve, and we're looking at the size, area, again in this case, of its projection down into a coordinate plane. Not a coordinate axis, coordinate plane. But it's still the size of a projection. So I think that's a pretty neat fact. By the way, given this inference, what do you suppose we ought to call this? It represents an area in the xy plane. I think dx dy is a pretty natural choice. If not for the fact that, now this is super sloppy, but there's this temptation again to do that. You know, it's notationally suggestive, right? It's not really mathematically, legitimate. But punchline is it gives us a reasonable punchline. So in fact, we are going to call this dx dy. So dx dy is the name we're going to give to that third coordinate of our vector differential. Now there are analogous arguments that you can make for the first two coordinates of the vector differential. That'd be a nice exercise for you guys to think about. Think about the piece of surface, and if you project that over into the YZ plane, and like so, and I guess an analogous argument. I think you can persuade yourself that these are what we should call those components. So all together then, here's where we were. Just from expanding, sort of multiplying out the formulas that we had for the ds vector, we had this formula. We tried to figure out, what reasonably should I call this thing, that third coordinate? How should I think about it geometrically? What should I call it notationally? Well, geometrically, it's the area of a projection of the piece of surface. And notationally, we've decided to call it dx dy. So this allows us, having rewritten ds as that ds we rewrite like that, a vector field of which we're doing a vector surface integral. Let's call its components p, q, and r, just like we did before. And notice what we end up with is a dot product of where we had coordinates. So I can crank out that dot product. And in a very analogous fashion to what we saw for vector line integrals, we have here an alternative notation for vector surface integrals. Does everybody see the analogy? I mean, if only in terms of how it lays out on the page, it's worked out very similarly to vector line integrals. Also very similarly to vector line integrals, these new kinds of integrals I've written down don't really immediately make sense. Right? We've never talked about an integral over a surface where you're multiplying an integrand times not the size of the piece of surface, not some sort of a dot product with a vector differential on the piece of surface, just this other thing. It's not even directly part of the surface. It's the size of the projection of the piece of surface. So it's a weird construction. It's a new thing. So we really technically need to write down a definition for it. So that's this, right? Definition of what it means to take an integral of a function over a surface, but with the differential being dx dy or dz dx, etc. So it's exactly what we talked about on the previous page. I'm just sort of writing down as a definition formulas that we've kind of already cranked out. Primarily, you're going to see this as an alternative notation for vector surface integrals. And again, we find ourselves trying to decide which one do we like better. Well, I think we like this one on the left better in terms of what we're going to be doing with it, in terms of how we think about these things. This is more compact. The objects in this notation on the left are more natural quantities, arguably. The vector field, that's a thing. That's something that we can kind of sort of relate to. The ds vector refers directly to a little piece of surface that we're visualizing as we try to understand integrals. Dot products make loads of geometric sense. We're like a lot of the stuff over here in this left notation. On the right, it takes at least 3 times as much space on the page. And individually, those 3 integrals are hard to infer a geometric interpretation of. It was not clear why we would ever want to do such a thing. Right? That being said, let me point out, just like with line integrals, this notation might not look very convenient, but this is highly suggestive. This is very similar to a very, very powerful notation, a very powerful idea called integrals of differential forms, with which you can do many extremely powerful things. So this is not bad notation. It's just not something that we're going to rely on very much in Math 212, just given the nature of this course. So you will see this notation. When you see notation like this, don't, in your mind, intuitively try to make sense out of these integrals one at a time, right? Because we don't have a really good sense for that. The better way, in my opinion, when you see something like this, is to view it as being part of a larger trio, and that the integrands here are simply the coordinates of a vector field for which you're doing a vector surface integral. So in other words, in some sense, when you see this notation, always translate back to this notation to try to make sense out of it. Okay. There are some details that I glossed over in the section here. I'm going to encourage you guys to read through those. For example, how to make sense out of the pluses and minuses. How does that have to do with the orientation of the surface, etc.? There's a discussion back here. It's analogous to what we saw with vector line integrals. Time being a factor, I'm going to let y'all read that on your own. Okay, so that's the end of chapter 5. Now on to chapter 6, our last chapter. This is a lot of stuff kind of all comes together in this chapter. Heavy topics here in chapter 6. I want to tell you a little bit about the approach that I'm going to be taking in this chapter. There are kind of 2 very common approaches for this material. There's a real challenge to multivariable calculus instructors to make a decision as to how are we going to present these ideas. A full discussion of these ideas, it really requires a sophisticated point of view that's just simply beyond what we can do in an introductory course. And that's just the sad truth. There are big, powerful theorems. The General Stokes' theorem and the de Rham cohomology theorem that are just way beyond what we can do in Math 212, and I wouldn't begin to talk about that in detail in this course. But that would be sort of the ideal. Okay, so what are we actually going to do? Well, we're going to talk about some special case theorems. Several special cases of these big theorems. And one approach that you can take, a lot of books do this, is to just enumerate the individual special cases, talk about them separately as individual special cases, and declare victory. And that's, there's an argument for that. There's a big disadvantage to that as well. The disadvantage is that these separate special case theorems, being as they are, in fact, all just kind of different manifestations of a single theorem, no surprise, they have a lot in common with each other. There are a lot of analogies, comparisons, connections between these various special case theorems that we're going to talk about here in Chapter 6. Right? So what I'm going to try to do here is, obviously I'm not going to actually do the big discussions. Right? But I'm going to present the special cases with deliberate points of view chosen in order to emphasize the analogies. I'm going to try to be vaguely suggestive of these results without actually being precise or rigorous, as that wouldn't be reasonable for this course. So there's going to be a certain amount of hand-waving and I'm going to say sloppiness a little bit. The idea being that I want to give you some glimpses of these comparisons and connections and analogies as much as I can without going too far and thus not being appropriate to the course. Okay, enough of that. So here's what we're going to be talking about. We're going to be talking about a bunch of different kinds of integrals. These are the domains on which we're going to be doing various different kinds of integrals. And in fact, we've already talked about integrals on all of these kinds of domains. We have talked about, in a single variable calculus course, integrals over an interval on the x-axis. We have recently talked about integrals over a curve in R2 or R3. We've talked about double integrals in R2. We've talked about triple integrals in R3. We've talked about integrals over surfaces in R3. Right? And I'm not using I'm going to sort of shy away from the term integral in this course because we also are going to need to make reference to points. And in particular, if you have a function, sort of a vacuous, sort of a trivial addition, that there's an addition involving only one thing. So it's kind of an integral in an extremely trivial sense. But if you have a function, and instead of a function and a curve, if you have a function and a point, you can say, well, let's just evaluate that function at that point. So I'm going to refer to these objects, most of which are integrals, as evaluations. So when you hear me say evaluation, you think integral. Now, which integrals specifically are we going to be talking about? Now, notice we have a couple of different kinds of integrals that we've talked about on curves. We are specifically, in Chapter 6, going to be talking pretty much exclusively about vector line integrals, not scalar line integrals. It just works out. The objects that we're interested in, these more lofty, sophisticated objects we're going to be looking at special cases of, those special cases are in reference to vector line integrals, not scalar line integrals. And likewise, vector surface integrals. Not scalar surface integrals. Okay. Going to need to talk about the notion of an orientation. We've already talked about some orientations. So specifically, when you're doing a vector line integral on a curve, here's a curve, right? And I say, here's a vector field, here's the curve, compute the vector line integral. Your first question has to be, well, wait a minute, are we going this way along the curve, or are we going that way along the curve? You're going to get different answers. The amount of work it takes to drive up a road, not the same as the amount of work that it takes to drive down the road. One's positive, one's negative, so they're different. Likewise, flux requires a choice of orientation. Which way? If you say how much fluid is flowing through the surface, do you mean in that direction or do you mean in this direction? Again, they're opposites. And the choice has to be made. So in both of these cases that we've seen, an orientation was something that it fits in with this definition I'm going to make here. An orientation was a convention. So it was a choice of direction. It was a convention concerning sign in an evaluation. In other words, one choice gives you one answer, the other choice gives you a minus sign. So two different options that are negatives of each other. So on a curve, there are two different directions along the curve. On a surface, there are two different directions through the surface. They're negatives of each other. So the thing is, we're going to need to talk about orientations, so conventions regarding sign and evaluations, for other kinds of domains where we don't have a geometric interpretation, like, which way are you going along the curve, or which way are you going through the surface. In these cases, I'm going to define orientation still now as a convention regarding sign and evaluation. It's just that the convention is not going to be geometric. It's going to be either, I'm going to call it a plus orientation, or I'm going to call it a minus orientation. And it involves sign in an evaluation as follows. Let's just look at a double integral here, for example. If I do a double integral, and if I infer my domain to be a positively oriented region, what I mean by positively oriented is evaluate it normally. Whereas, instead, if I have a negatively oriented region, what I mean by negatively oriented is I want the negative of the integral. So this kind of mimics these geometric notions of orientation we've already talked about. Again, on a curve, you can go that way or that way. They give you negative answers of each other. On a surface, you can go through that way or through the other way. They give you negative answers of each other. Here we don't have a geometric interpretation, but I have two choices of an orientation. They give me negative answers of each other. And this is going to end up being important and useful. Okay. So it's a weird convention. So we're going to lose the air quotes, by the way. That's just for sort of emphasis in that original introduction. This is how we'll be writing such things most of the time. I'll just write a minus sign in front of a set. A minus sign in front of a set means I want to view that set as negatively oriented. Okay. We're going to be writing down stuff like this. I'm going to be, in particular, making a reference to a domain that is a sum of two other domains. It means exactly what you would hope, namely, doing an integral over a sum of two curves. Well, you're going to do an integral over the one curve, and then subsequently you're going to do the integral over the other curve, and you're going to add them up. Just like you would sort of kind of expect. Okay. So now there are some conventions that we have to choose. I have to talk about what the word boundary means. We kind of already know what a boundary is, right? I mean, if I give you a two-dimensional region, I can talk about the boundary curve of that region. Here's the awkwardness that we find ourselves in, though. And that is, let me draw a picture here. If I take this two-dimensional region, and if I ask what's the boundary of this two-dimensional region, I gave myself a lot to fill in here. Okay. Finally. Okay, if I give myself that two-dimensional region and ask, well, what's the boundary? Well, the boundary is a curve. You can kind of see the curve. There's the big question, which orientation do I put on that boundary curve? So we're going to have to make some choices. That word boundary is now a loaded word. Boundary, henceforth, I have to interpret what I'm taking a boundary of as being an oriented thing. So this two-dimensional region, I have to know, is that a positively oriented or a negatively oriented thing? And given that, I need to further be able to deduce the boundary curve oriented which way. There's two different ways I can go around this set, right? And I need to know which way do we mean. Okay. So I'm going to tell you what the conventions are here. These are arbitrary conventions, but they're very classical conventions. Everybody does it this way, right? So even though they are arbitrary, it's important that we do them the same way as everyone else. Just otherwise, it creates problems, right? That makes sense to everybody. Nevertheless, arbitrary. If you look at the conventions I'm about to give you and think, what's the point of making that? Couldn't we have done it the other way? Yes, absolutely. Okay, so here they are. We're going to start off with an interval on the x-axis. What's the boundary of an interval on the x-axis? Well, it's 2 points. Sure. Right. Okay, but in terms of orientations, what convention are we going to make about the orientations on these 2 points? Keep in mind, orientation on a point is either a plus sign or a minus sign. The arbitrary and yet extremely standard choice is to refer to the right endpoint as positively oriented and the left endpoint as negatively oriented. Arbitrary choice. Now there's some good ideas behind this choice, but there are other choices that also have those good ideas. Anyway, this is the choice that we're going to stick with. Is everybody good so far? Okay. Fine. Next question. Suppose I have a curve in R2 or R3, either. So here's a curve. Now keep in mind, this is an oriented curve, so it comes with a direction. There's an orientation on that curve. Given this oriented curve, and here's again the big question: 1, what is the boundary? And 2, what is the convention that we should make concerning orientations on that boundary? Well, the boundary consists of these 2 points. I'm going to refer to this one here as the starting point because of the way the curve is going. I'm going to refer to this one as the ending point. So I've got a starting point and an ending point, and the choice is the starting point you orient with a negative, the ending point you orient with a positive. Arbitrary choice. Some nice consequences come from this, but nevertheless, it is an arbitrary choice. Highly standard. Is everybody on board? Yes?
So the orientation of the starting and ending points is different than the orientation of the curve itself?
Well, there's really no comparison to be made. It's an apples and oranges comparison because an orientation on a curve is a choice of a direction. An orientation on a point isn't, right? It's just really hard to compare them. Yeah. I guess they're different in the sense that they're not the same, right? But they couldn't be the same. Is I guess the point I'm making. Do note that this convention kind of smacks of what we did here. Namely, you can view this interval as having a direction, and you can view the A as the starting point, negatively oriented, B as the ending point, positively oriented. So they're kind of consistent choices. Okay. Next question. Region. Two-dimensional region here. And I've deliberately punched some holes in this region to make its boundary a little harder to talk about on purpose. So there's a two-dimensional region. The boundary consists of, well, in this case, these 3 curves. And, yeah, fine, but what's the orientation on those 3 curves? Well, the choice is very often misunderstood. The choice, I'm going to start with the outer piece of curve. Very often, and this is not 100% accurate, students will say, oh yeah, always orient boundary curves counterclockwise. And you can see here, the arrow that I've drawn here, counterclockwise. And it is counterclockwise for that outer curve. But counterclockwise is not a general rule that always applies. The general rule that always applies is this. Wherever you should happen to be on the boundary, when you are going in the correct direction along the boundary, the region is on your left and nothing is on your right. So you're always going to go in the direction such that as you go in that direction, the region on your left side. And notice it doesn't always give you counterclockwise. Look at, for example, on this piece of boundary curve here, which direction would I go around that in order to, as I go, keep the region on my left? I'll go clockwise. Anybody see that?
Would it matter in that one?
I'm sorry?
Would it matter in that one?
Oh, yeah, absolutely. Because if I go the other way, if I go, suppose I were to go that way, then the region is now on my right. You got to turn your head upside down, right? So you got to imagine yourself, walking along, right? And yeah, exactly. Okay. Arbitrary choice, highly conventional, very important that we stick with it. Okay, what about a three-dimensional solid? Again, this is one that's very often misunderstood. Here's whoops, I messed up my own solid. This is a kind of a ball. This is not a full mathematical ball that I'm drawing here. This is a ball with a hollow hole in the middle. It's a racquetball, right? So it's got a certain amount of thickness to it, but there's nothingness on the inside. Is that fair enough? So on the boundary, for example, look at the outer boundary here. Again, common mistake is to say that the orientation is always outward. It's not really right. What is always right is that the orientation is always pointing away from the solid. So note that this is the direction from the boundary that takes you away from the green as opposed to into the green. But notice what happens on the inner piece of surface, the inner piece of boundary. I'm going to have to go to the pencil here. On the inner piece of surface, you have to go inward to go away from the green. Right, so it's not always outward oriented. It's always away from the solid. Sometimes that's outward, sometimes that's inward. Does everybody see the difference? Now here's the hard one to talk about. What if you have a surface in 3 space? So this is again, I made up a deliberately weird surface here. It's got holes in it. It wraps under itself. Terrible surface. Surface has a boundary curve. What's the orientation on the boundary curve? Here's the answer. So your surface itself. Keep in mind, I need to know what the orientation is on that surface. That surface is going to come with itself an orientation in the form of a normal vector. Okay. So what you're going to do is you're going to take that normal vector, move it out to the outside like that. Right? And then you're going to ask a question very much like the question that you that we did for 2-dimensional regions, namely, which direction do I walk to make sure that the region is on my left? In this case, the surface on my left. So this being, let's think of this normal vector now as me. So there's me, right? And as I'm walking in the correct direction with my head, importantly, at the head of the normal vector for the surface, and my feet, importantly, at the tail of the normal vector for the surface. Which direction would I walk to make sure that the surface is on my left? And you can see there's only one direction here. If I walk as directed in the direction of that red vector, the surface is on my left. But if I were to turn around and walk this way, the surface would be on my right. Can you see the idea there? Now, imagine trying to make sense with this out of which direction the orientations go on this. You're going to be imagining yourself on this little piece of curve here, upside down and backwards and walking the opposite direction and trying to keep track of which way is left and right. It's a nightmare. I encourage you not to think about it that way. Here's a better way to think about it for situations like that. And that is, keep in mind, again, your surface comes with an orientation in the form of a normal vector. Bring that normal vector not all the way over to the edge, just near the edge. And let your thumb of your right hand point in the direction of that normal vector. And notice which way your fingers curl. So that, what you do with your right hand, your thumb, and the direction that your fingers want to curl is going to define what I am going to loosely call a swirl around that normal vector. That swirl sideswipes the boundary in the correct direction. That make sense? So now let's go back to let's look at, here we go. Let me zoom in on this very quickly. Let's try to make sense out of what the orientation should be here. So for example, let's look at this point. Start with that point. Here's my normal vector. And think about that normal vector. In what direction would swirls, with my thumb pointing in that direction, looking at my finger curl, the swirls are going to go around kind of like that, which sideswipes at that point in that direction. Pretty good? And thus, we have this orientation on that piece of surface. Now, you can just carry that orientation all the way around. Now you have the orientation of that entire sort of outer curve. Yes? However, what about at this point on that other little piece of the boundary curve? Well, again, same normal vector now. Think about which way the swirl goes. Well, the swirl kind of goes around like that. Well, that side swipes up against this piece of curve in that direction. And it looks kind of opposite. I mean, it's a little bit disturbing. It sort of feels like, well, look at these two pieces. I mean, this one's going that way, but that one's going that way. And it's tempting to say they're going opposite directions, but they aren't going really in opposite directions. They're different, totally different pieces of curve. Those directions don't really have a comparison. So, no contradiction at all. That makes sense? Yeah.
So why does that inner circle go the way that it does?
Yep, because of the side swipes. So let's. So there's a normal vector. Think about which way our fingers curl when we do that, right? And so I can't zoom in any more than this, but so when if you look at that point, the swirl is going that way, and at that point, that side swipes the curve in that direction. Yeah. And if you don't like, arguably this point is awkward because there's a sharp turn happening there, so you could bring your normal vector over to, let's say, there, and again do your swirl, your side swipe, and it side swipes in that direction. Yeah. Okay. And now, just to show you the advantages of this versus the whole on your left, imagine yourself walking point of view. Let's try to make sense out of which way the orientation goes at this point here. Nightmare of confusion if you do it with, imagining yourself walking, but the normal vector is like that. Okay, I'll come over here, and it's like that at that point. Now, no problem. Right hand thumb down because your normal vector is pointing down. So point your thumb in the direction normal vector does, and just imagine now look at which way your fingers swirl. And your fingers swirl that way. And that side swipes, and again my picture's gotten full, but I think you can see it side swipes along that piece of curve in that direction. Like that. Everybody on board? Okay. So that's the tough one. So that's how orientations of boundaries work. Arbitrary choices. Important that we stick with them. So let me show you what we've got so far now. Now this is a diagram summarizing objects of interest. There's a lot of ideas that run around in Chapter 6. I think it's important to keep them organized. Categorize, organized. It's a pretty good word here. So what I have here is 3 separate diagrams showing you what's going on in R1, R2, and R3. You'll notice that in each of these spots, in each of these diagrams, there's various different kind of integrals. We have sort of one-dimensional integrals in R1, which are single variable, classical single variable integrals. We also have kind of one-dimensional integrals in R2. Those are vector line integrals, like so. Right? And we have one-dimensional line integrals in R3. Again, vector line integrals, like so. Likewise, two-dimensional integrals. They're double integrals if you're in R2, but they are vector surface integrals if you're in R3. And if you're talking about a two-dimensional domain in R3, flux is our object of interest. Talking about a two-dimensional region in R2, that's just a double. Okay, et cetera, various different kinds of evaluations at different points. We've talked now about what boundaries mean. Note that a two-dimensional region in R2, its boundary is a curve in R2. What we're going to find, it's pretty cool actually, we're going to find that there's a relationship between these kinds of integrals. And I don't want to go too far ahead all at once. By the way, we already know one of these. We know that there's a relationship between these kinds of evaluations. Namely, you can evaluate a single variable calculus integral by plugging in appropriately to the right, you've got to find the right function, but if you plug into the right function, plug into the points A and B, you can evaluate an integral. So we already know this kind of a connection. We're going to find analogous connections involving boundaries in all of these other contexts. So we're arguably going to find 5 separate new theorems, all of which can be thought of as generalizations, sort of extensions of the fundamental theorem of calculus. I hope that sounds like a big result, because it really is. These are huge results that the fundamental theorem of calculus, this thing that did so much for us in Math 111L, Math 112L, etc. So many powerful applications. That's the tip of the iceberg. Right? And there are two-dimensional versions of it, three-dimensional versions of it. Depending on which kinds of integrals you're talking about, there are lots of variations of it. Said differently, it's a special case of this much more powerful general theorem. So, the little cultural note, the fundamental theorem of calculus, well, I'll do it like this. Fundamental theorem of calculus, that connection is a special case. All of these new theorems that we're going to talk about in Chapter 6, they're all special cases. What they're special cases of is called the general Stokes' theorem, or Stokes' general theorem. And it's a theorem about integrals of differential forms, these things that we can't really talk about in this course for a more abstract kind of thing. But the Stokes' general theorem includes all of these statements and arbitrarily more at higher dimensions. So we're going to be talking about them individually, but again, I'm going to try to show the comparisons and analogies between them as we go. Okay. All right, so I'm going to begin that by reminding you about the fundamental theorem of calculus. I know that you guys all know the fundamental theorem of calculus. as we often do, the point here is not to make sure you know it. The point here is to set up the right point of view that's going to make it generalize well. That's going to make it, that's going to segue for us best into this multivariable setting. So I'm going to take a point of view on fundamental theorem you might not have seen before. Maybe you have, maybe you haven't. But this is the point of view that I think is going to be really most useful for extending. So here's our context. We have an interval from A to B. I'm going to try to make sense out of an integral. You know, what can I do with an integral on that? We're going to kind of come at it backwards. But you know that the first thing that we do is we chop it up into little pieces. Right? Okay. All right. So I'm going to be interested in an integral on that domain, and we know what the result is. We know that we're going to be able to relate it to an expression that looks like this, involving an antiderivative. But let's see how we get to it. Okay. So again, we're going to go at this backwards. I'm going to start actually by looking at f of b minus f of a. Let's start by looking at the kind of the answer. And I'm going to try to get from here and reproduce the integral. So, in order to do that, I first want to go back up here. Well, I'll do it. Yeah, okay, sure, I'll put it here. I'm going to look at this interval, and let's talk about its boundary. So the boundary, I'm going to do orientations with colors. I'm going to use, actually, let me, let's see here. I'm going to use yellow for the interval. I'm going to use green for the starting point and red for the ending point. Street sign motivated. All right. So green is negatively oriented, and red is positively oriented, given the convention on orientations that we talked about. Okay, fine. So it's positively oriented B and negatively oriented A. Now, next question. What can I say about the orientations on the individual pieces? Well, let's look at I1. There's I1. I'm offsetting it up just to keep my picture from getting weird. What's the boundary of I1? Well, it's a negatively oriented starting point and a positively oriented ending point. Fine. What about I2? There's I2. Negatively oriented starting point, positively oriented ending point. Okay, cool. I3. Go. Stop. I4. Go. Stop. Okay, now you might notice here that, in fact, there's kind of a connection. If I were to take all of these boundaries and add them all up, well, I got a bunch of points. The boundaries of I1, I2, I3, I4 involve all these, x1, x2. These lots of little points in there. But let's look at x1, for example. In that sum, x1 appears twice with opposite orientations. Likewise, x2 appears twice, but with opposite orientations, etc. Most of the points in here appear twice, but with opposite orientations. The only 2 points that appear only once, and therefore don't have sort of an opposing bizarro version of itself, right? Are the starting point A, which you'll notice appears only once, negatively oriented, and then the ending point, which appears only once, positively oriented. So lots of cancellation on the middle, exactly the same things on the outside. So the punchline here, and I've got this written out in different ways, but the boundary of the interval as a whole is the sum of the boundaries of the individual subintervals. It's kind of weird, right? You take all of You take all of these, and if you add them up, you get exactly the boundary of the interval itself. Okay. Now, algebraically, you can see that here. And that is, if you were to do an evaluation, if you were to say, okay, fine, let's take these points, these oriented points, and do the evaluation. Let's plug them into the function f and see what happens. What is f of each of these? Well, there's f of the boundary of the whole interval. The boundary of the whole interval is there's a positively oriented b and a negatively oriented a. The negatively oriented a is why we have a minus sign there. One at a time, if I do the same thing on these subintervals, I get these various terms. And there's the same cancellation. So in particular, let's look at the next term here. The next one is f of x2 minus f of x1. And notice that this this positively oriented x1 cancels with this negatively oriented x1 there. And they cancel. Just like we saw over here, sort of more geometrically. This is sort of the more algebraic point of view on it, but same result. And so the punchline is that this is what we call a telescoping sum. So all of these terms here, most of the terms, everything in the middle cancels, and only sort of the outside terms remain. So this fact is going to be our foot in the door to creating an integral. So in particular, this change that I've started with, that change can be thought of as the sum of the little micro changes over each of the intervals. That's not that surprising of a concept, really. I can stick a limit here on the front for free. If something's true, it's certainly true in the limit. Okay. Now you look at this and think, well, gosh, that looks kind of like an integral, but not quite. I need a delta x on the end to make it an integral, so I'm going to multiply and divide by delta x, just as an excuse to get a delta x there to go with everything else to make this look like a Riemann sum. And then notice, and this, I'm going to sweep some formality under the rug here, but that, in the limit as n approaches infinity, kind of suggestive of a derivative. It turns out that you can call that the derivative, and this is fine. So yeah, I'm sweeping some rigor under the rug there. Yeah.
Quick question. The symbol in front of I, like way up on this page, it's the same sort of partial symbol?
Oh, yes. I'm sorry. I should have talked about that. Thanks for asking that. It's a great question. Yeah. Let me find that. Here's the first place I used it. Yeah, we use that little partial symbol to represent boundary. Yeah, no, it's a great question. So, very common notation. I'm going to be using it quite a bit in the rest of this book. But we've seen this symbol previously only for representing partial derivatives. It's also a way to represent boundaries. Yeah. Okay. So, nice punchline though here. The change that we started to compute, we see here we can compute it as an integral of f prime. And by the way, there's a couple of, here's one point of view. I'm going to be hitting this following point of view pretty hard as we go further on into Chapter 6. But the very first step here was to observe that change accumulates over the interior. So right off the bat, now we don't think of change in that way. We think of change as something that happens on the boundary. You have a starting value of the function and then an ending value of the function. You look at those two values. Change means subtract those two values. But what we see in this equation here is that change accumulates over the interior. It's weird. Normally we think of stuff like mass. Mass accumulates, population accumulates. If you have a grand total amount of mass and you chop it up into little pieces, the total of those masses equals the mass of the whole thing. That's the notion of accumulation we've thought of in the past, and that's good. The weird thing is we see here, change. This is a very abstract concept of change also accumulates. It's a little bit weird, but here it is. Change is computed with an integral because change accumulates. Okay, so I'll come back and talk about that a little bit later on. Okay, so what has happened here, the sort of general strategy, maybe let me celebrate a little bit more on our result. We started off with an interval and its boundary. What we have found is that given a function, there is an operation that you can do called the derivative such that, let me write it down here. Given an interval and its boundary, there's an operation that you can do to a function called the derivative such that this kind of evaluation of the given function on that boundary interval equals this kind of an evaluation of that derivative function on the original interval. So a point of view that we can take on, this is sort of a new point of view we can take on the derivative. The derivative is the function that sort of is complementary to the notion of taking the boundary of an interval, in that the boundary of an interval, the derivative of a function, give you this setup to where the left side and the right side evaluate in exactly the same way. Okay, so all of the boundary theorems that we're going to talk, all of the generalizations of the single variable fundamental theorem of calculus that we're going to talk about, all of the special cases of Stokes' general theorem, they're all going to have the same kind of pattern. We're going to be looking at boundaries. We're going to be trying to make sense out of what kind of an operation can I do such that the left side will evaluate the same as the right side. And we're going to be successful in all these attempts. Okay, the strategy is going to be very similar in all of them. I'm going to start with looking at a particular object of interest. Where did I put it here? Yeah, particular object of interest. In this case, we were looking at change. There are different objects of interest that we'll be looking at in these different contexts. We're going to then break up the region, note that it accumulates, make some analogous kind of arguments, and come to our conclusions. Okay. All right, so that's sort of the roadmap of much of what we're going to do in Chapter 6. Okay, I'm going to give you the first example here. This first one comes actually pretty easily with this idea in mind. It's called the fundamental theorem of line integrals. It's very much like the fundamental theorem of calculus, thus the name. But it is different. It's importantly different. Okay. So instead of looking at this part of the picture, instead of looking at the one-dimensional picture, we're going to be looking at the two-dimensional picture and focusing on this part of it. So we're going to start with a curve whose boundary we're going to look at. That curve will have a boundary consisting of 2 points. Okay. We're going to ask the question, can we motivate some way to do something to a function such that when I evaluate on both sides, I get the same answer? And it's going to come about by looking at boundaries again. So here's our curve. That curve has a starting point and an ending point. And I observe that this boundary is the same as the sum of the boundaries of the individual pieces. In other words, if you were to look one at a time, there is our first little piece of curve. It's got a starting point and an ending point, oriented accordingly. The next little piece of curve has a starting point and an ending point. The next little piece of curve, you can see where I'm going with this. Next little piece of curve has a starting point and an ending point, and we get the exact same picture we had in the previous fundamental thermocalculus exercise, and that is that there's a bunch of interior points. They all appear twice as parts of the boundaries of the pieces of curve on sort of opposite sides, one positively oriented, one negatively oriented, and they cancel. Really very much the same picture. And so just like in the single variable case, the boundary of the curve is the sum of the boundaries of the individual pieces. In terms of how that works, how that manifests itself in algebra, the change in the value of this function f that we're interested in, that change over the entire curve is just the sum of the changes over the individual little pieces of curve. So here's a silly sort of physical example. Let's look at this picture again, and let's try to keep. Maybe this is a road that we're driving along, and let's think of the function as being altitude. Well, f of b minus f of a says what's the total altitude gained of driving along the whole road? I'm pointing out that is the same as the amount of altitude gained on the first piece of the road plus the amount of altitude gained on the second piece of the road plus the amount of altitude gained on the third piece of the road. This is highly plausible if you really think about it. Does that make sense? So change accumulates. Here we're seeing change accumulating over a curve as opposed to over an interval on the x-axis. Okay. So here this is written a little bit differently. Change accumulates. Total change is the sum of the individual changes. If something is true always, then it's true in the limit. So I can put a limit in front of this. Now I start to see how this is looking kind of, sort of, roughly, kind of like an integral, not exactly. The algebraic next move here is a slight variation, but let me just point out that on a little piece of curve, we already have a formula for how to compute change. This is a chapter 4 result, old chapter 4 result. The change in a function, change in an output, is gradient dot change in the input. An old fact about directional derivatives.
So why did you put the limit in front of the delta x5?
Oh, because I'm just trying to make, you're asking about this integral right here, or this limit, because I'm trying to make this change end up looking like an integral. And that's really kind of my goal. It's just selfishly motivated, yeah. And realizing that change of an output is gradient dot change of an input, now I've got that expression, and that is exactly a Riemann sum for which that we made as the definition of this vector line integral. So we have proved, in some sense, the fundamental theorem of line integrals, that is equal to that. Now you can view this two different ways. I like to derive this particular theorem kind of backwards in the sense that I started with f of b minus f of a, and then I work that back to being an integral. In practice, the way we use this most of the time is, hey, if you're given an integral, if you're given a vector line integral that you'd like to compute, here is a super handy-dandy formula for how to compute that vector line integral. Does that make sense?
When we're given like vectors and stuff, will we know that it's given in the grid?
Yeah, that's the big question. Yeah, and I am going to have to talk about that. So let me momentarily not answer your question. We're probably not going to be able to get to it just right this second. The first thing I want to do is get an application under our belt. But you have an excellent point there. So specifically, let me make your point a little bit differently. Note that this only applies to vector line integrals of gradient fields. Only gradient fields. Right. Okay, so I want to do one quick application. Well, let me celebrate again first. And notice that what we did, we started with a curve in space, 2 space, with boundary points. we started with a function, and what we have found is that the gradient operator is the operator such that this kind of evaluation of the original function on the boundary curve gives you the same result as this kind of an evaluation of the gradient field over the original curve, namely that. So, in terms of how it looks on these diagrams, really similar to the fundamental theorem of calculus. Right? And different operators are playing different roles. Here we're talking of boundaries of curves being points as opposed to boundary of interval being points. Here we're talking about the gradient, not the derivative, the gradient. Different context, different operator makes the thing work. But the punchline is the same, is that this operator, this gradient operator, is playing a role that's kind of complementary to the role that boundary is playing in that it makes these two evaluations work. A very quick and easy example. Suppose I want to compute a vector line integral. Suppose my vector field is this one. You might recall that this is very similar to an integral that we worked out back in Chapter 5. When we first wrote down vector line integrals, we computed a vector line integral of something that looks a lot like this. And we did it the old-fashioned way. Right? We parameterized the curve, and then we plugged into the formula, did the whole pullback thing, and then we ended up with a single variable integral where we had to fundamental theorem of calculus, find an antiderivative, etc. Fair amount of work. The clever move here is to realize that this vector field is the gradient of a particular function, namely that function there. And that as soon as you realize that your vector field is a gradient of a known function, then you can plug into this handy-dandy formula, namely take the two endpoints, A and B, plug into this anti-gradient function that you just found, f of b minus f of a, and there's your answer. And that's what I've done here. Having found that anti-gradient, plug in with the two endpoints and subtract, done. Don't have to parameterize anything. You don't have to compute a resulting single variable integral involving, as you might recall in that previous example, sines and cosines, and wasn't that bad, but nevertheless it was a certain amount of work. Here, plug in, spike the football. Okay, good place to stop. See you guys later.